Great. So again, welcome to our Turing-Roche Knowledge Share Series event. And the aim of these monthly events are to bring together members of the Turing, Roche, and the wider scientific community to hear different perspectives on topics in data science and build new connections. As the partnership research progresses, we'll also be regularly showcasing this at future events as well. So to get us started, I'm just going to share a couple of slides on the partnership. Hopefully you should all be able to see that. So if I go to the next slide. So the Alan Turing partnership, the clue's kind of in the name of this one. So the Alan Turing Institute, hopefully you've heard of one of the organizations, was established in 2015 as the UK's National Institute for Data Science and AI. We're a network of 13 universities, and we also have a number of strategic partnerships. Roche is our first pharmaceutical partner. And then Roche was established a long time ago as a leading healthcare company. They have a long-term interest in personalized healthcare, and they also have a number of academic partnerships, which we're part of. We collaborated first in 2019 in a Turing hackathon, and we launched our 5-year strategic partnership in June 2021. And this is our partnership kind of North Star, our kind of guiding light. So ultimately, we're collaborating to explore this term, patient and disease heterogeneity. So why patients respond differently to treatment and why diseases manifest in different ways in different people. Doing this through advanced analytics. As you can see, there's a lot of different research areas and activities we can kind of be exploring over the 5 years. We've chosen kind of 2 research themes actually so far, and you can actually find out a bit more about our current activities on our partnership page, which you can find on the Turing website. And what's also not reflected in this North Star is the connections and the collaborations we want to build. So it's really critical for us to be running events like this to get the community involved. And today's event theme is Explainable AI in Health, which is really key for us as a partnership. We expect to be developing tools and algorithms as part of our research, and it's critical that we can interpret these and give transparency on how they work. So I'm delighted to welcome our 2 speakers today who will be giving us insights on how explainability plays a role in their research and the benefits of this. So we're joined by Boushehri, who is a PhD student at Roche, and Antonella Perini, who is a research associate in data justice and global ethical futures, which is part of the Turing Institute's public policy program. As mentioned, we'll be hearing from our speakers, and then we'll be having a dedicated Q&A session. Should be plenty of time for questions. So you can ask a specific question to either of our individual speakers or a more general question on explainable AI for both of them to answer. So I'm just going to stop sharing now. There we go. So with that, I'll hand over to you, Ali, if you're ready.
Thanks, Vicky, for the intro. And yeah, I'm Ali. Nice to meet you all, meet you basically, and I'm really looking forward to this presentation. Yeah. I'm a PhD student at Roche, and this is actually my PhD project that I've been working on for the last 3 years. Yeah, so looking forward to actually presenting. So the topic for today is a brief intro to explainable AI and its application to antibody screening. This talk has 2 parts. The first part is just intro to explainable AI and just motivate the ideas, and then the second one would be basically the main project that I worked on within my PhD. And as a bit of motivation to explainable AI, in the recent advances that we have in machine learning, we had actually very great advances recently, especially in the task of diagnostics. And in many cases, they actually reach the human level or even outperform experts in diagnostic tasks, such as, for example, in detection of myeloid leukemia, or for example, in the pathology, they actually reach via self-supervised learning better than human annotators sometimes. And also in other diseases, such as Alzheimer's disease, for example, in terms of diagnosing the Alzheimer's disease, the actual and prognostics they actually reach very high level of accuracy or performance. However, due to the black box nature of the algorithms that they're using, none of them they really reach to the clinical use, and still many people are trying to work on that area. So as a practical example, let's imagine that we have trained an algorithm that can discriminate between myelocyte and typical lymphocyte. Well, what they are really doesn't matter, just how these cells they look like. So we have two cells normally, and due to the different actually technical variations, the images might look like this. One of them has like a yellow background, the other one has some other color, basically, and the content of the cells are also different, the cell types, basically. And imagine the algorithm can actually predict which image belongs to which category. But then, as a human, when you want to actually look at the results, the very first question that you have is that, did the model use simply the background color as a discriminator? And the other one is that, what's the exact difference that the model has noticed between these cells? Is it just the color? Is it the cells around the main cell? Or is it actually the shape and morphology of the cells? And that's, in a sense, is actually the motivation of using explainability, to understand what the model is really looking at, and then be able to trust the predictions. Otherwise, one cannot simply, trust the model that just using the simplest, explanation for predicting the cell types here. In general, the classification pipeline that we have, for example, based on this problem, is that you have like a series of images, and they belong to different classes. And the very first type is that actually you do feature extraction, which can be done either using handcrafted features, for example, cell size, texture of the image, etc. Or you can actually use a pre-trained model or some sort of autoencoder for feature extraction, and then use classification. The second setup is that actually if you use deep learning classifier, which is a method that, for example, using the input images as well as the annotations to extract the features and then try to predict the images, predict the cell type in the images. And if you have them together, the question would be that, how can we explain each pipeline here? So for the very first type that you have this pipeline of feature extraction and classification, the very first type of explainability is that in model, and that's in such a way that you choose a model that has in model explainability, or intrinsic characteristics of the model can be explained. For example, you have a random forest which looks at the gene index, or linear models that's simply the coefficients of the linear model that you have can be used as some sort of explanation. That which features, for example, are very important for a specific prediction. And then there are methods such as called post-model that, for example, they use shape values, which is a game theory-based method, or permutation importance that actually you permutate the values in a feature and try to see how much drop in the performance you have. These are some of the most famous, for example, methods that are out there, but there are actually there are also downsides to it. First of all, they need meaningful features. For example, cell size and cell texture, these are meaningful features, but actually if you have some abstract methods for extracting features, such as feature 1, which is an abstract with no physical meaning, or feature 2, and your model says, well, the second feature is more important than the first one. Well, great, but that doesn't really tell you anything here. And that's important to actually to know what you're looking at, like in terms of the biological meaning in this context, for example. The other one is that they suffer from high dimensionality, these methods. If you have like 500 features, 1,000 features, and while it says that 100 of them are important, great, but what can we really learn from 100 important features? I mean, that might help you, but still, it's not gonna be the most, informative thing. And also they suffer from multicollinearity. For example, if the cell size and the cell texture, they are correlated and the algorithm says one of them is important, you really cannot say that the second one is not important because they're fully correlated anyway. So that's for the first type. And for the second type, if you have a deep learning classifier, the most basically famous method that people are using these days are basically using post-model pixel importance type of methods such as GradCam, LRP, saliency methods, etc. And normally that gives you a heat map or like some sort of pixel importance or value of importance per pixel. And for example, for the case of a cell detection, well, it normally gives you that basically where the cell exists is the most important one, hence red, and the rest they're not as important, hence blue. And they work quite great as sanity checks. However, they cannot provide meaningful insights, or at least they suffer in like providing meaningful insights. For example, in the work of Matek et al. In 2019, they show that actually their classifier can work as good as a human expert. And when they look at the saliency map of actually that model, they see that, well, the model is looking at the cells as well as the other cells on the side, in the background. And that's the only thing that the model is actually providing. That's really good to be sure that the model is actually looking at the important parts of the image, but that doesn't really tell you how, for example, it can discriminate between monocyte and monoblast. And that's a downside of using such models at this point. So what I want to say is that there are many types of way of actually doing explainable AI, but that really depends what you want to do and what you are really looking for. If you are really looking for if you are looking for understanding the concept or the biology, most of these methods actually they have their own downsides, and especially deep learning still lacks the great the sufficient explainability at this point yet. So that's why when we are using deep learning, always one has to find some sort of way of some tricks to actually provide explainability, but still there are always downsides or some problems in just using them as some sort of method. So that was the first part of the talk, just to go over the methods that they are out there. And now the second part is an application in antibody screening. That's basically the PhD project that I did. So the use case that we had was that to use explainable machine learning for profiling the immunological synapse and functional characterization of therapeutic antibodies. That's a lot of buzzwords basically there. I try to explain them a bit more. So the motivation is that the formation of an immunological synapse is the first event of adaptive immune response, an immune reaction between the T cell and antigen presenting cell. That's practically one of the most important things that happen in body. And so far, the mechanism and modulation of antibodies are still quite unclear. It's been years that people are working on it, but we have a lot of questions that they haven't been answered yet. And so far, no study has systematically addressed how quantity and morphology of the immunological synapse is correlated to T cell function. And there was no universal tool at the time when we started to work on the project. Now there are a few actually. But on the time, there was no universal tool for working on imaging flow cytometry data. However, our tool is really focused on providing explainability here. Now, after a lot of words, maybe actually let's really get back to biology and try to simplify what was there. For an immune response, normally you have an antigen presenting cell and a T cell with a specific antibody to that antigen. And when these cells, they interact, the receptors, they get closer to each other, and then information is actually flew between them. And we call it immunological synapse. And if you look at the cytoskeleton, normally you see that actually the concentration of the cytoskeleton, we have a higher concentration of cytoskeleton in the proximity of each other. And the task that we had was to understand this basically, which is still quite scientifically unclear. So that's basically the main task here. And as any machine learning project, well, we need the data, like a lot of it. And practically this part of this plot, that's the recording part. And we use imaging flow cytometry, which is a high throughput imaging technique. And you can actually, for example, record thousands of images within a few seconds or minutes. So that was really useful. And we chose this technology because it actually enabled us to do to understand like a statistics of the data and also do like significant tests, because normally that's like one of the problems in biology. And we recorded more than 3 million images. So that was a very big data set that really helped us with analysis. And as you see, this type of technology actually provides multi-channels. So it's not 3 channels RGB normally, but actually the images might have up to 12 channels of actual information there. So how can we classify the cell types automatically? We developed a Python package, a modular Python package to extract the interpretable features. So for example, if this is the image, bright field is just a normal image, or like normal microscope. We have F-actin, which is a cytoskeleton, MHC2, which is a biomarker for B cells. CD3, we use it as a biomarker for T cells, and phosphorylation as a biomarker for synapses. And we extract features such as morphology, intensity, colocalizations, such as Pearson correlation, Manders overlap coefficients, and Jacquard index, and synaptic features, which they were based on some information from the field. And to actually enable training a classifier, an expert basically spent quite some time to actually annotate the images. She annotated 5,221 images, and these are the classes that she came up with. So you have the classes of single B cell, which is actually which is a class that you only have a B cell and only shows MHC2. Then there is a class with T cells without a signal, which is a class that only shows CD3, and then there are T cells with a signal which also show phosphorylation. And then you have doublets, which are more interesting classes. Now you have a B cell and T cell in one class or in one image. And there are like different basically variations, but the most important one is a synapse with a signal. And that's here, that you see a B cell with blue, you see also a T cell with green, and also in their synaptic area, they also show phosphorylation. It's a very small data set actually compared to what we had as 3 million images. And also the important part is that this distribution does not actually reflect the correct distribution of the data, but this is just what we got as the annotation. Okay, then we trained multiple models on it, interpretable features plus XGBoost, ResNet 34 versus deep learning, ResNet 18, again, deep learning, deep flow, etc. And we showed that actually the interpretable features plus XGBoost worked on 33% of the data as the holdout set. And ResNet 34 wasn't as good. We kind of expected that because we didn't have a lot of data. ResNet 34 did not work better. But in general, interpretable features reached a very great amount of performance, and at the same time, it provided in-model explainability, as I mentioned previously. And these are the most important features that simply tells us that if you have a correlation distance of MHC2 and CD3, that was the most important feature. And that tells you that there are at least 2 cells in the image. And then, for example, with 3 cortosis, that can tell you that if there is a signaling in the image or not. And then, for example, things like cell size, they come up as important. And most of them, they were really in alignment with biology of the problem. Okay, and the very last part, now that we can actually classify the images and the cell types, now we want to understand the synapse formation part. And the question is that, can we use explainable AI to profile the mode of action of therapeutic antibodies on synapse formation? And as a proof of concept, we studied an immune response activator. So this is the setup that we had. We added the B and T cells together. And as a control, we added an antibody that does not provide any reaction. But then on the other side, we added an antibody which actually increased the immune reaction. And for that, we use a CD19 TCB. And now we tried it for 6 donors in 2 different experiments. Experiment 3 and 4 here is shown with different colors. And the very first thing that we observed is that adding actually the CD19 TCB led to higher concentration of synapses as well as multi-synapses. And that's, as a proof of concept, that made sense because That's what we expect. When we add an activator, the CD19 TCB here, we want more, we want to see more synapses. So that was a very good sanity check. And then something that was new, now we looked at the morphology of the cells, and we observed that in every case, significantly, actually adding the CD19 TCB led to a higher enrichment of phosphorylation affecting and MHC3, the synapse region. And that was something new using the image data, at least in this field. So as a summary, we created an end-to-end pipeline to study immunological synapse. And we use Explainable AI to actually study immunological synapse properties in an unbiased and systematic way. And this image-based approach actually made a lot of sense because the features that we found as important, we were only be able to capture them if we used imaging data and not like other methods such as flow cytometry, which do not provide imaging data. And the tool can be used in other imaging flow cytometry data sets and applications. Thanks a lot for listening to my talk. And yeah, I hope that was interesting.
Thank you so much, Ali. That was great. We will now pass over to Antonella, and then we will be having a Q&A session at the end. I will pop the Slido chat link in the chat again if anyone wants to ask any questions, and take it away, Antonella.
Thank you. Okay, let me know if you all can see the...
Yeah, no, that's great.
Great, that's always the main question, isn't it? Well, greetings everyone, and thanks first of all, Vicky, for organizing this space, and Ali for your presentation. I think both presentations will be quite complementary in a way, and looking forward for the Q&A later. So to give a bit of background about the talk and also how I will structure, for the past month, along with some of my colleagues at the ethics team, Mike Smera, Janice, Morgan, and David, we have been working on the topic of equity in medical devices. So in this talk, I will first present our findings, an overview of that work, and then I will draw on the ethics team work on AI explainability, a work that has been done mainly through Turing Commons and Project Explain that some of my colleagues have worked on. So I can address, how explainability is critical to respond to equity challenges in medical technologies. So diving into the work on equity in AI-enabled medical devices, our project started as a rapid review for evidence from an independent review panel appointed by the Department of Health and Social Care on the extent and nature of the existing biases in these devices and the existing instruments to reduce or prevent the risks of such biases. So we conducted a rapid literature review in the time frame of 4 months and complemented our desk-based research with 25 semi-structured expert interviews. Also, we had some key concepts that were very relevant to our work and also that I want to make explicit in the presentation. First of all, health equity, which describes an ideal within a society in which all members are able to experience their full health potential. And this was transversal, of course, to our work. And then the second key concept is that of social determinants of health. So while one's biological and constitutional features play a significant role in influencing our health potential, there are also other non-medical aspects that are social in origin and can be potentially modifiable that also play have an influence on our health potential, which can be, for instance, working conditions, housing, education, or sanitation. And we employed a 4-quadrant model inspired by one developed by Leslie and colleagues that we used to conceptualize the key literature that we were reviewing and illustrate also how biases and inequity can enter into the medical technology ecosystem as cascading effects. And so I will walk you now through each one of those quadrants. So first we have the world, that is the social and historical reality that precedes or comes before the design of the medical devices. And here, as you see in the icons, the real world patterns of inequity and discrimination are can manifest in various forms, for instance, unequal access to care or biased medical training. And failure to consider these patterns in AI projects can lead then to inequity at every stage of the AI lifecycle. So for instance, if a system is not designed to attend to social determinants of health or is trained with data containing implicit biases from clinical notes, then it can perpetuate healthcare disparities. The second quadrant is the data used to train, test, or validate the AI-supported medical technologies. So here, inequities can enter the data through various means. For instance, if we have insufficient representation of certain population groups, if there's lack of data quality or completeness, if there's inadequate coding practices. So for instance, clinical workload or hospitals that are under-resourced or are not digitally mature may be unable to collect data in a reliable or consistent way, or similar, like some coding practices that may not capture the nuances of socially constructed categories like gender or ethnicity. So for example, studies, some of the studies that we have reviewed show that minority ethnic groups are more likely to be overrepresented in the not known or other categories in hospital data sets. And what does this entail? It entails that it obscures patient needs, that it limits appropriate screening, diagnosis, or treatments. The third quadrant is the design here. It represents the socio-technical design, development, and deployment lifecycle of the AI system. So there are many examples here, but just to name a few, like from power imbalances that shape research agendas and problem selection to failure to evaluate differential performance, which lead to disparate impact. And then the ecosystem. So here we mean the economic, legal, cultural, political sphere. Inequities and biases at this level can steer or shape AI-based medical innovation. So for instance, when health technologies are provided by companies whose business interests sit in tension with equity-driven healthcare policies. So in simple terms, the unvirtuous circle in a way demonstrates that when health-related AI innovation ecosystems do not prioritize equity and bias mitigation, the real-world patterns of discrimination and equity, so those emerging in the first quadrant that I mentioned, will be encoded in the data sets used to train the health technologies, so the second quadrant. So as a result, those technologies will reproduce injustices. And these injustices will also, these technologies will also augment and compound them. Will augment and compound these injustices through discriminatory bias that enter at the point of design, development, and deployment of the life cycle, so the third quadrant, and also discriminatory bias that emerge at the ecosystem level. And so the resulting harms continue to cascade and perpetuate, further, for instance, exacerbating real-world health disparities, which will then in turn generate discriminatory data over again. So now moving to the main topic or central topic of this talk, let's focus on some of the challenges to equity and responsible research and innovation, which might help, or the explainability might help to address. So first, as observed, inequity can enter the AI life cycle through various points, leading to embedded bias in medical devices. And to mitigate these biases in health and healthcare, project teams can implement different techniques. And they also need to account for the social and historical features of the medical technologies ecosystem. AI systems in the sector also need to be compliant with corresponding regulation or standards to which medical devices are subject before they are approved, and they need to demonstrate such compliance. Also, to protect patients from various types of harms, including those identified in our review, there are a series of mechanisms that can be put in place, from risk management activities to effective remedy of those who are negatively impacted by an AI system to redress harms. And fourth, the autonomy of marginalized patients may be at stake as a result of their oppressed status, exacerbating in a way inequities shown in our review. So one specific way this happens is when patients are not given meaningful or situated information, or are given information that is restricted to that the healthcare provider considers is relevant. So here there are risks of indirect paternalism and the reduction of the degree of autonomy of patients to choose the treatment. So what is common here is that explanations are critical to respond to these equity challenges. So explanations can help understand the model and how decisions in the life cycle have been carried out to detect and mitigate biases. Explanation has a role also to play to understand, for instance, where data came from, explain to the people collecting the data how it will be collected and what it will be collected for. Explanations can also help to demonstrate compliance, to exercise the right of redress in the case of patients negatively impacted by a system, and also provide meaningful information to patients for them to trust their capacity to choose effectively. So how can explainability contribute to making sure that AI-enabled medical technologies provide reliable outputs? And here, and this is, part of the work done from the team working on Turing Commons, where it in a way also manifests and illustrates part of our approach to explainability in a socio-technical approach, where explainability can be defined, and here I will read it, as the degree to which a system or set of tools support a person's ability to explain and communicate the behavior of the system or the processes of designing, developing, and deploying the system within a particular context. So note here the reference to the importance of the context. Explanations are situated within a specific context that has its own expectations of what constitutes also an acceptable explanation. And the distinction between outcome-based and process-based explanations. So here, like outcome-based explanations would mean those that clarify the result of a specific decision. It explains the reasoning behind a particular outcome. And process-based explanations, which aim to demonstrate that you have followed good governance processes and best practices throughout the AI lifecycle. To support the goal of explainability, there are three key factors that I want to maybe communicate here or share. So first, interpretable models. So, the degree to which a human can understand the cost of a model's prediction or behavior. So here, while I won't focus on this, it is worth highlighting that in the context of responsible research and innovation, selecting the right interpretability methods can help us in not only, it helps us in many other objectives, such as accountability and transparency, or even better understanding our data. Then we have project transparency. This is the process that helps explain and justify the actions and the decisions that were taken at every stage or at different stages of the project life cycle. And as we have seen, the focus of an explanation may not necessarily be exclusively at the model level, but also at the level of the project governance or the data pipeline or other aspects of the AI life cycle. So we may need answers for questions that will be relevant for explanations, such as what is the source of the data, how was integrity, quality, and completeness of the data evaluated, how decisions about the biases relevant for the project were taken, and why any chosen mitigation strategies are sufficient to address them. And this brings us to the last key aspect, which are situated explanations. It is crucial to have an awareness of the sociocultural context in which the explanations are required. So questions around what do we need to explain and who do we need to explain this to are key guiding questions that will help us through the task. So I'm considering maybe the equity challenges that I mentioned before. Explanations for bias detection and mitigation tasks may be different and address different stakeholders, to say explanations to inform patients about an AI systems that might be put in place for a certain treatment, or explanations for redress. Some explanations may require explaining the why of an AI decision, others the who is involved or who to contact for a human review of a decision, the what of a decision or the steps taken to ensure bias is mitigated, among other things. And each of these explanation types serves as different purposes when considering the needs of the stakeholders it is being delivered to. So to wrap up, and again, as I mentioned, this was like a really nice opportunity to bring together the work of different projects in our group. And there are mainly three key messages that I want to highlight. So in the final section of what is for the moment, the forthcoming reports on equity in medical devices, we provide a range of bias mitigation techniques that have been offered in the literature to ameliorate the risk of inequity in AI-enabled medical devices. And technical bias mitigation is important and should be part of the system development cycle, but it is also essential to consider whole of society and multi-sectoral approaches to technology governance. So this requires understanding the history and the context issues that affect health, that affect healthcare, and the development of technical tools for this domain. The second point is, as observed from the unvirtuous circle, inequity can enter the AI life cycle in many ways, including through technical decisions, but also from the social aspects that surround the technologies. So this requires a socio-technical approach to responsible research and innovation, which accounts for both outcome and process-based explanations, as well as situated explanations that I mentioned before. And then the third and final point is that the cascading effects of inequity will also mean that explanations will also have compounding effects. So this encourages, in a way, an explanation-aware approach throughout the AI life cycle. And this explanation-aware approach starts with, at the moment of the design, before the development of the medical device, selecting priority explanations during plan formulation by considering context, and hopefully creating a virtuous circle. Thank you so much, for listening to the presentation. We'll be having this next minutes to answer questions, but you can always send me an email or even like through the Slack channel that is provided. And I understand the presentation will be shared, but in any case, I will be also sharing with you some of the resources that are listed in this slide, which some of them are outcomes from the projects that are exclusively related to explainability. One of them is Project Explain, which has an outcome, which is a guideline on how to explain decisions made with AI, specifically for organizations. And also there's a Turing Commons skill tracks on responsible research and innovation, which has the components and some of the things that I've mentioned in my presentation. Thank you.
Thank you so much, Antonella. That was great. I feel like we got there like molecular level and then all the way up to the real world level from both presentations. So hopefully you all enjoyed that. I will pop the Slido link again in the chat for any questions. Feel free actually as well, if you want to put up your virtual Zoom hand to ask you a question live, you're also more than welcome to do that. If not, I will get started with the Slido questions. Oh, Ashish, would you like to go ask a question first, and I'll do the Slido ones next?
Hi. So excellent talks by both speakers, and question for Antonella. So great presentation again, and I was wondering, so one piece that really caught my eye was situated explanation. So often, especially I am based in India, and India patient populations are very diverse, right from the top of the socioeconomic pyramid who have knowledge, have education, and with educational privilege, which allows them to be able to interpret and make educated decisions about their health, and also the very bottom of the pyramid who often are not educated. So for a complex disease, like given a cancer diagnosis, I was just curious, have you looked at that? How do you structurally design mechanisms to kind of level out the playing field for all kinds of patients, especially in the context of AI. Like I'm being given a diagnosis based on an AI model. How do I make an informed decision about the diagnosis I have been given?
Yeah, that is a very relevant question. And yeah, so as I mentioned, situated explanations, I mean, here, stakeholders may be varied, may be diverse. So we also need to take into consideration that diversity. And even if, for instance, healthcare professionals might need help in tailoring or thinking about these different explanations for the patients. And I think, yeah, that is like a very relevant thing that you mentioned, how we are not considering this, or we kind of think like that patients are homogeneous, they are heterogeneous, and at the same time, there are inequities in how they, as I mentioned before, like different instances of oppression that might already put them in an unequal position when receiving this information. And I think this is like one of the things that we need to consider when deploying systems, AI systems in the healthcare sector, and also providing, as I mentioned, like explanations for those who are going to use the systems and those who are going to be affected by the systems. And here, one of the things that we always kind of advocate for is stakeholder engagement processes, where we need to receive, the inputs and be in contact with those who are going to be affected by the systems, understand what are the needs also in terms of explanations. And here, hopefully, we will find that those explanations we might need to tailor to the specific situations and contexts.
Just a quick addendum. Often the developers of AI systems are very different from the users, and the users who are clinicians may not know the intricacies of the models. So one solution that has been proposed by others is using model cards, which convey at a high level the efficacy and accuracy and risks of using a model. Have you looked at model cards in your research?
No, unfortunately, yeah, I cannot give you a response on that. But yeah, if there's anyone in the room actually that has worked on that, yeah, it would be interesting to see what their opinion is. Thanks.
Thanks both, and thanks Ashish for asking those questions live. I'll switch to the Slido ones, but again, feel free to put up your hand, anyone else. I guess a question we've got a kind of like a couple of forms of is kind of, how can we evaluate the results of the explanation models in the healthcare field to trust them? And so another question is, research has kind of shown that different explainable models such as SHAP, DICE, and so on result in different results based on the same data. So how can we trust their explanations? So I guess a question to both of you about that kind of meta explain on explain. I don't know, Ali, maybe if you want to take that one first.
Yeah, so if I understand correctly, it's like, how can I trust different methods of explainability? Or yeah, if I got it, how can we trust their explanation? That was the question basically. That's actually that's a very tough question, to be honest, to answer, and that really depends on the question at hand. So what you really need to do is that probably look at a few of these methods, or at least like if you have the option of looking at, if you have a random forest, I would probably look at the feature importances right away, and at the same time look at maybe SHAP values and like per samples. And the other thing that might be interesting or useful is that to actually use domain knowledge to, how can I say it, to actually accept or reject some of this, feature importances. So not, some of them might be right away pretty interesting, but actually like an expert needs to be able to, say that actually that was a good, observation, or no, that was just like a random, coincidence. And I think that's quite important. So for me, I would always try to actually consult some experts on the domain, and then like try to see which one of these, feature importances actually are the best ones, or at least closest to the reality.
That makes sense. Antonella, I don't know if you want to add anything from your perspective.
Yeah, I think that was, I mean, he's the one with a more technical profile, but I think, yeah, I mean, I think one of the main things as well is like documenting why the decision and why you would think, yeah, whether something is providing enough explanations or not, or is providing enough assurance in a way. I think that the documentation of that and the decisions, that is a key thing.
Great, thank you. Ali, a specific question for you. Do you have any general advice on generating a set of interpretable features for a classification task?
Mm-hmm. Yeah, absolutely. So a set of features, I mean, that can mean a lot of things, but here I assume like explainable ones, at least, or interpretable ones. So if I'm working on images and I really want to understand the biology of the question at hand, I would try to actually just stick to the ones that they have physical meanings or biological meanings, and then try to train a model which can be explained easily. At least that would be the first thing to try. If you really care about the performance, and then that's a very tough question to answer, because most of the models at some point they become black boxes, or like, for example, like, deep learning models, and then that becomes harder and harder to interpret. But at least as a starting point, I would suggest that stick to biology and do something which is a bit easier to understand, and then after that move to something more complicated or more sophisticated, let's say.
Great, thank you. And Antonella, one for you. Are you currently supporting the NHS or other public health organizations in the adoption of explainable AI? And if so, how?
I mean, I'm only responding for answering from the ethics team, because there might be other groups at the Turing who might be doing that. So yeah, that is also maybe a note. But from our group, we're not currently doing that. What in terms of explainability, as I mentioned, there's this project on Project Explain, which was done with ICO. So it was a very comprehensive guidance on how organizations can implement explainability in their projects, and that has been done exclusively. It was like a collaboration between ICO and the Hellon Turing Institute. And again, I will post the outputs of that work, because there, I mean, we go through different principles, the different types of explanations, some of which in a way I've tried to be into the presentations, but they're like kind of a taxonomy of explanations, as well as more like kind of practical tips or guidance on how to implement explainability in organizations.
Perfect, thank you. I think my Zoom is just freezing a bit as well in case I cut out. I hope that you can still hear me. The next question is for both of you again. Do either of you use any vendors such as Clickworker or Mechanical Turk to train and or maintain algorithms to generate explainable AI? And is a no from Antonella. Anything from you, Ali?
As far as I'm aware, no, but that might be some part of also the organization that might do that. I don't know.
Cool, thank you. Yeah, I hadn't heard of those either. And the next one, I think one for you, Ali. How does your work in clinical oriented machine learning feed into basic research like early stage drug discovery and drug target identification?
Yeah, thanks a lot for the question. That's really good one. Our actually work is mostly focused on drug screening or like antibody screening. So what in the like a drug discovery, actually our work wouldn't be exactly relevant, but then when they, for example, they have like some antibody candidates and they want to see which one, for example, performs better, or like a specific thing that they are interested at, then our work would be actually interesting or relevant there.
That makes sense, thank you. Antonella, actually, we got this one from our Slack earlier, so they haven't seen your talk, but hopefully, I think it was maybe something you touched upon. So kind of about the legal requirements for explainability in AI in healthcare, if there are any at the moment, and if not, kind of what you would recommend is the best way to kind of manage the issues that arise from a lack of transparency.
Yeah, so I mean, where systems use personal data or make decisions about individuals using personal data, we can apply UK GDPR and Data Protection Act, which impose in a way certain requirements for explainability. So UK GDPR requires personal data processors, including developers and deployers of medical devices, to provide information about what data is collected, how it is used, or who it is going to be shared with. And also, yeah, UK GDPR and Data Protection Act like informs certain rights on individuals, such as of being provided information about the logic of a decision, or the consequences potential consequences that might have for them, or even the right to object the data being processed. So that is one thing. And then there's and this was also relevant for our work on equity in medical devices, the UK Equality Act, which prohibits discrimination on the basis of certain protected characteristics. So organizations in a way have to, or whoever develops or deploys these devices must ensure that any AI used to make decisions don't discriminate on the basis of those protected characteristics. So that is one thing. In terms of, like, for instance, standards, I do not recall anything of the sort, like, but again, if there's someone in the room who knows about that, like, yeah, please refer to that. And again, NHS, MHRA, I remember reading some of the guides from developing medical devices, AI-enabled medical devices, and they refer to the Turing's and ICO's guidance that I mentioned before.
Perfect, thank you so much. I think we maybe just got time for one last question. I think we actually only have one left in the Slido. Again, I think probably for both of you, but how do you counter anthropomorphism and confirmation bias, i.e. using prior knowledge, we'll be looking to find confirmation for an explanation that makes sense. And that's a bit of a challenging one. Ali, I don't know if you want to take a stab at that first.
Yeah, tough question, actually. At least, like, in our field, what we do is, first of all, try to provide, how can I say, like, a few different data sets, and use, like, from different cohorts, or, for example, with different characteristics or different batches, or with different technical variations, and then see if actually our model or our findings actually, they are, how can I say, you can extrapolate to the new data set as well, and then yeah, basically use it as a validation of what you do. Also, in general, that's how can I say, that's also best practice to use an orthogonal method to confirm what you found previously, or like you use a different method of data generation, or like a different method in general, to actually see if what you observed was also can be also observed in other data sets. So that's at least how we do it. But of course, that's, again, how can I say it, prone to bias, and that, it's not exactly perfect anyway.
No, that makes sense. Thank you. Antonella, anything to add from you?
Yeah, no, that is such an interesting question. And, while we were doing this literature review, we encountered so many of these confirmation biases at different points of the life cycle. So basically, I mean, how to solve that is so difficult. I think that the main thing is to, like, consider that might be one of the entry points for biases. And who was the authors that mentioned? I think it's Pot and other colleagues, because I don't want to say something that I haven't said, but this is, like, very interesting, and like the concept of fairness through awareness. And I think that is one of the key things. I mean, we know that these biases might get into the devices we're developing or deploying. Knowing that might be a chance, like, makes us already think, like, okay, how can we spot this? So, like, also asking for other colleagues to help us go through I mean, awareness already is one of the key steps, the first steps, at least.
Yeah, that makes a lot of sense. Thank you so much. I think we're coming to a close now. I think we got through the majority of questions. I'll have a check if there's any extra ones. But in any case, both our speakers are in our Slack workspace. So if you want to contact them there or ask any extra questions, feel free to do that. I'll just post the link again if you want to join the Turing-Roche Slack workspace. Thank you so much to both our speakers for some really fantastic talks and a great discussion as well. Our next meeting is going to be